Time series analysis focuses on understanding patterns in data observed over successive periods of time, such as interest rates, inflation, stock prices, or economic indicators. Unlike cross-sectional analysis, time series analysis emphasizes how observations evolve through time and seeks to identify predictable structures that can be used for forecasting. One of the most common patterns observed in financial and economic data is a trend, which represents the long-term direction of a variable. Trend models help analysts estimate future values and evaluate economic developments. In CFA applications, understanding trend behavior is essential for forecasting macroeconomic variables, company performance, and market conditions. A linear trend model assumes that a variable changes by a constant amount during each period. The model is estimated using ordinary least squares, OLS, where time itself serves as the independent variable. The intercept represents the estimated value at the starting point, while the slope coefficient measures the average change per period. Positive slopes indicate upward trends, while negative slopes indicate declining trends. Linear trend models are useful when changes occur in absolute terms and growth remains relatively stable over time. Analysts frequently apply these models to forecast economic indicators, sales, capacity utilization, and other variables that exhibit consistent long-term directional movement. A log linear trend model is appropriate when a variable grows at a relatively constant percentage rate rather than by a constant absolute amount. In this specification, the natural logarithm of the dependent variable is regressed against time. The slope coefficient approximately represents the compound growth rate of the series. Log linear models are particularly useful for financial and economic data because many variables, such as GDP, corporate earnings, and asset values, tend to grow exponentially over long horizons. Compared with a linear trend model, the log linear approach often provides more realistic forecasts when growth compounds over time and when percentage changes are more meaningful than absolute changes. An important requirement for time series modeling is covariance stationarity. A covariance stationary series has a constant mean, constant variance, and stable covariance structure over time. When a series is not stationary, historical relationships may not remain valid in the future, making forecasts unreliable. Trend models are often used to identify and remove deterministic trends that contribute to non-stationarity. Analysts must evaluate whether the underlying economic process remains stable and whether structural changes have occurred. Failure to account for non-stationarity can result in misleading statistical results and poor forecasting performance, even when the model appears to fit historical data well. Autoregressive (AR) models extend time series analysis by explaining the current value of a variable using its own past values. In an AR1 model, the current observation depends on the immediately preceding observation, while higher-order models such as AR2 incorporate additional lag values. The autoregressive coefficient measures the strength and direction of persistence over time. When the coefficient is positive and significant, shocks tend to persist across periods. AR models are widely used in finance and economics because many variables exhibit serial dependence, meaning that past behavior contains useful information about future outcomes. The effectiveness of an autoregressive model is evaluated through residual diagnostics and forecasting accuracy. Residuals should exhibit no significant autocorrelation if the model adequately captures the time series structure. Analysts compare alternative AR models using out-of-sample forecasting performance, commonly measured by the root mean squared error, RMSE. Lower RMSE values indicate more accurate forecasts. However, analysts must also recognize coefficient instability, as economic and financial relationships often change over time due to regulatory shifts, market developments, or structural economic changes. Consequently, model selection requires balancing statistical reliability, forecasting accuracy, and economic relevance to ensure that predictions remain useful in real-world investment applications.